Nernst equation. The Nernst equation is a new equation for us because it relates electrochemical cells that are not at standard conditions. Here's an example of a concentration cell. You notice, first of all, the molarities are different. On the left here in the anode, we have a 0.1 molar silver ion solution with a silver electrode. And on the right, we have a 1 molar silver ion solution with a silver electrode. And of course, the anode loses electrons and the cathode gains electrons. And when there's a deposit of some sort of metal on something, it's always at the cathode end. And again, a concentration cell is one where the same ions are on the side, the same side, and have the same components, but different concentrations. The Nernst equation, a useful equation, is this one here. And I'm actually going to show you how we derive the Nernst equation. So notice the fancy E equals E0 minus 0.0591 over N log Q. How do we get that? Well, you will remember, and I'm going to get my pen. No. You're going to remember this equation, which is delta G equals delta G0 plus RT ln Q from the previous chapter. And from the previous section, delta G equals minus NFE. F, as of course, is a Faraday. And delta G0 is minus NFE0. If I replace delta G in this equation and delta G0 in that first equation, what do I have? Well, I have minus NFE equals minus NFE0 plus RT ln Q. Dividing both sides by negative NF, I end up with E equals E0 minus RT over NF, and I'll make the F the Faraday fancy F, ln Q. Because T, which is the temperature, is at 25 degrees, the R, which is the gas law constant, and the Faraday are all constant, and factoring in log and ln, when this is reduced at 25 degrees to a number, it can be therefore fully reduced to what you see over here. Or, as you can see, log K at equilibrium, because Q equals K at equilibrium. And I think of Q or K as simply the concentration of the products over the concentration of the reactants. So let's look at an example. And there was not one on this PowerPoint slide, so I had to make one up, which of course is always dangerous. So let's look at an example of the Nernst equation. Here's a reaction. 2 aluminum plus 3 Mn plus 2 AQ yields 2 Al plus 3 AQ plus 3 Mn solids. So under normal conditions, we could find, if this was 1 molar solutions at 25 degrees, we would use the standard reduction potentials, and we could find E0 cell pretty easily. So when you do, you realize that one of the numbers, of course, has to be flipped. So when you look up Mn plus 2, you get negative 1.18 volts. When you have aluminum, that one is the one I believe that has to be flipped. I'm flipping through my book now to determine where it is, because I looked it up earlier and I just want to make sure I am correct, which we'll find out. So Mn plus 2, yeah, is negative 1.18 volts. Aluminum is negative 1.66 volts. So obviously obviously, to make it work out and to make it match the equation here such that aluminum solid is a reactant, I need to flip the sign of what's negative 1.66 volts to be positive. So when I add, I can produce positive voltage. Remember, these are reactions that are spontaneous. Spontaneous reactions are ones that occur without intervention and therefore have positive voltage. So under normal conditions, it would, and 1 molar concentration, it would produce 0.48 volts. So what would happen if we changed around the concentrations? Well, let's look at Mn. If Mn was 0.50 molar and aluminum was 1.50 molar, obviously both of those concentrations are different than 1 molar. And let's think about Le Chatelier's principle for a minute. If I decrease the concentration of Mn and increase the concentration of aluminum ions, think about the imbalance there. I've decreased the reactant and I've increased the product. Which way will the reaction shift in order to reach equilibrium, or in order to establish its previous equilibrium? Well, if I add more products and reduce the reactants, the reaction is going to shift to the left. If it shifts to the left, there's going to be less products produced. What would that do to voltage? Well, remember, voltage is produced if the reaction can go as seen here. If the reaction shifts to the left, the reaction can't go in the direction you see here, and therefore voltage should decrease. Which is a way to think about it. But the Nernst equation not only helps us think about it, it actually helps us solve for what the new voltage should be. So how do we get that? Well, remember, E cell equals E0 cell minus 0.0591 over N log Q. And N stands for number of electrons involved. You might have to write the two half reactions to figure out how many electrons are involved. But you can also notice here that this has a positive 6, and this is a positive 6 because manganese is a 2 and aluminum is a 3. So that would eventually have to be to produce 6 electrons on each side to cancel. That's actually the number of electrons here. Happens to be a 6. If you can't see that quickly, and oftentimes they ask you to write the two half reactions anyway, you should probably write the two half reactions to figure out N. Alright, so E cell, how do we get it? E cell equals E0 cell. Now I've already gotten that, 0.48 volts. And I got that, of course, from the standard reduction potential chart. Minus 0.0591 over 6 log Q. Now Q is the concentration of the products over reactants. Remember, of course, solids are not included. So I'm only really interested in the 1.5 to the second power, remember the 2, divided by 0.50 to the third power. When that's all finished, and you resolve it and use your calculator, you're going to find that E cell is equal to 0.47 volts. Now, you might not be impressed that it's kind of close to the E0 cell, but also know that the voltage did go down. So we were able to predict in advance, by knowing Le Chatelier's principle, which way the reaction is going to shift. But now we actually have some firm data here with the Nernst equation to say what that voltage is actually going to be. So let's look at the difference between E and E0. Well, you saw it before with the Nernst equation. What is that? When is E equal to 0 and when is E0 equal to 0? E is equal to 0. That means in the Nernst equation, if you solve and you get 0, when is that? Well, that's when the cell is at equilibrium. and you have actually a dead battery. When is E0 equal to 0? That's that concentration cell. E0 is equal to 0 for a concentration cell. So let's look at this question. You make a galvanic cell at 25 degrees containing a nickel electrode in 1 molar nickel, silver electrode in 1 molar silver. This is a standard cell. Notice you wouldn't need to use the Nernst equation for this question. Sketch the cell labeling the anode and the cathode, showing the direction of the electron flow, and calculate the cell potential. Very common question that you will see. Alright, so how would we do it? Well, we have to look up some information. So usually the first thing that I would do if I saw something like this, I of course know I'm going to have, my two, there's my salt bridge, solutions. Usually the anode is on the left and the cathode is on the right. I'm going to have a piece of metal. One of them will be nickel and one will be silver. And then there's going to be a wire that's going to connect those, and electrons will flow in this direction. So that's pretty easy. But now we have to figure out what's in the anode side, what's in the cathode side. So I will go to my standard reduction potential chart and just look up the information. Nickel plus 2 electrons yields nickel is on there, and that's positive 0.23. So is silver, of course. Silver ion plus an electron yields silver. When I look that up, it's 0.80. They're both positive. So I have to add them in such a way that we're going to get positive voltage, because this is a galvanic cell. You'll see a little bit later in another video about a electrolysis cell. And if that word is there, then you do something quite different. But a galvanic cell is one where voltage is produced naturally. So therefore, to make this work, I'm actually going to have to flip this reaction around, and therefore it's going to be negative 0.23, and when I add it together, I should get 1.03 volts. And that's how you solve that kind of question.